Hi everyone, my name is Zhong. I'm from Carnegie Mellon University. I work closely with Professor Alex Waibel. I'm here to present to you our work on low-resource translation. As a motivation, let us talk about this picture where an American father is teaching her daughter to wash hands. And these other children in Africa are also learning about washing hands. What's so important about washing hands, you might ask? Well, 2 million people can be saved each year because of the simple hygiene practices. The number is much higher because of the pandemic last year. To close the gap between the girl on the left and the boys on the right, translation can help. Our research goal is simply information dissemination. We translate from rich resource languages into low resource language. And we do this under 3 constraints. The closed text is known in advance and is massively parallel across all source languages. The target language is severely low resource. We have quite a few challenges. Most of the multilingual works limit their data based on available data or the researcher's intuitive discretion, and are limited to less than 30 languages. Most works require more than 4,000 lines of low resource data, and many works use rich resource languages as hypothetical low resource languages. There is also an inherent variable binding problem with any neural architecture, where Zhong calls Mary is different from Mary calls Zhong. And most works present final translation results as sets of translations from all source languages. We address these challenges one by one. Firstly, we rank and pick most useful source languages from 124 languages in a principled fashion. 2, we use 1,000 lines of low resource data. And in addition to using English as a hypothetical low resource language, we work with a Mayan language, Eastern Pokomchi. It is actually ranked as our class 0 as one of the most severely low resource languages in the world. And we build an auto-preserving named entity translation mechanism to solve the variable binding problem. We build a novel method to combine all translations into one. Firstly, let's talk about ranking. We rank 124 source languages by building a word replacement model. And we replace every source word with the most probable target word by using this probability. It has 3 components. There is the alignment probability, and the probability of fertility equaling 1, and the probability of distortion equaling 0. We have a few terms here. So we use FAMO to denote the family of origin, which is the linguistic family. And we use FAMO plus to denote the expanded version of the linguistic family. In case there are not enough languages from the same family of origin, we would actually include a few languages that are in close by families. And we use FAMC to denote family of choice. And there are 2 family of choice that we introduced in this paper, one by distortion, the other one is by performance of the word replacement model. And we show some examples here. So on the left, you can see Eastern Pokomchi's neighbors, and on the right, you can see English's neighbors. And FAMD is by distortion, and FAMP is by performance. We can see that the languages from the family of origin are starred in this ranking as well. You can see that the languages, they overlap, but they're not necessarily the same. In the past, the state-of-the-art machine multilingual transformer tags the source sentence with the source language and the target language label. And we can see here as an example, we have English translated English to Indonesian. And to translate that, we tag the English source sentence with the English source label and the Indonesian target label. And in this way, the multilingual transformer is able to translate it into Indonesian with ease. However, over here, you can see that Andika and MIC, these are named entities that are not taken care of separately. And And in the case when the named entities are very rare and when there are many of them, this is not working. So we need a better solution. So in our model, we actually have built a multilingual lexicon table that covers 124 languages. And Dika and Nick, instead of being funneled into the transformer, we actually mask it with our NE0 and NE1 and translate. And the final translation is decoded by our target dictionary and then returned to the Indonesian. So in order to do this, we have built this table, lexicon table, that covers 2,939 Bible named entities in 124 source languages. We include many of the rare named entities that only occur once in the text and covers more than 66 severely low resource languages. To talk about our model, we need to talk about two configurations. One is a multi-source, multi-target translation, and what we call a complete configuration. And the second configuration is actually a star configuration, is multi-source, single target. So with that, we can talk about how we train our model. In the first stage of the pre-training, we pre-train on all the neighbors with the whole text. And in this actually takes some time. And in the second stage, we pre-train on the complete configuration of the 1,000 lines. Notice over here, the data is symmetrical because we only take the 1,000 lines from each of the source languages that is aligned with the low resource language data that we have. And for the final training, we train on the star configuration of this 1,000 lines from the lower source language as well as the source all of the source languages. And note that in every stage here, the data is symmetrical. And finally, we combine all the translations by ranking their centeredness. The centeredness is defined by the sum of the distances from the one translation to all the other translations. And we present the highest ranked translation. And in this way, we get the final combined score. We have two datasets. One is a Bible dataset. The other one is EMEA Dataset, which is a medical dataset that is very helpful for the pandemic. So over here, we can see that using English as a hypothetical low resource language, our family of choice performs much better than family of origin. And for Eastern Pokomchi, our family of choice by distortion performs better than FAMO. And we also have this performance against baselines here. So we can see that iterative pre-training on semantic data performs much better than those that without pre-training or with only one stage of pre-training. And it outperforms the asymmetrical baseline by more than 10. Note that the asymmetrical model basically uses the same amount of data, but it doesn't arrange the data in a symmetrical way in different training stages. It just trains everything at once. So we can see that our model is better. So these are the qualitative evaluations. Some of the examples, you can see that named entities are translated very well. And out of curiosity, we also tested on the whole Bible. So in a way, we take a randomly sampled 3.5% of the Bible and train based on that, and then test on the rest of the Bible. We reach a combined score of 31.3. For our EMEA dataset, we also have very high scores. And we can see that the qualitative evaluation is very well. And even though there are some situations, for example, infants and cattle, these are not translated very well. I think it's mainly because of in the training data, there is the cattle is actually not in the vocabulary. So that might cause the problem. And in the future, we would like to work with native speakers who speak the low resource languages, for example, the Mayan language, Eastern Pokomchi. And thank you so much for your time.